Welcome back to High Performance Computing, Advanced Scientific Computing. Today we have our lecture 7 on distributed deep learning and applications. So this is a lecture which builds substantially on material of lecture 6. So we will review this before we then come to the idea of distributed deep learning. Hence, in reviewing what we had the last time in lecture 6, we learned about the simplest learning model that you can have, the linear perceptron model. It's a linear learning model because it's linear in its weights. You see that a little bit in the idea of the perception of the perceptron learning model here. But before that, we even said to build this, what we largely consider today as neural networks. They are called artificial neural networks, ANNs. We also had to make, let's say, a sort of assumption, which was a supervised learning assumption. Hence, the focus on the last lecture was really on supervised learning, meaning that we have for all the variables where we have, basically data from some guiding output for its label. For instance, you remember the flower classification. Is it Irisitosa or Irisogenica? So 2 classes, for instance, and for each of these points and data points of these different flowers, we would have this guiding label, Y, making it then essentially this vector notation of all the features you would have, peta width, peta length, etc., like from the flower last time, per flower, and then in each of the flowers, you have not only the features, basically this feature vector of this particular data item, but also then the guiding output that we can use them across the whole data set, right, that we have here. In analogy to our problem, we had also then explored further. We had the MNIST data sets, handwritten character recognition, which is then from 0 till 9, hence a kind of 10 class problem, right? So then that means we basically have here the input, which was essentially then this, handwritten character. We have seen it in 2D, if you remember the last time, which was a sort of problem for the initial perceptron learning model and the neural networks, because we do a large, let's say, input vector here from a 2D problem. Hence, we have to vectorize or basically put it all in one long array to put an input to the perceptron learning model, where we had the ideas that we also, have this kind of linear, decision boundary, if you want, right? So basically, what you see is playing around with a line here, sum up linearly using weights, the idea of the data, and putting then even the bias that you have basically in the equation for, let's say, a linear decision boundary also as a part of learnable problem. For mathematical convenience, you can actually put this a little bit in this notation as X transpose W, where X then transpose means essentially putting again a long, vector here inside, and the weights are anyway the trainable, that's why they're red. The idea is that we have to learn here through iterations, going over this data set again and again with different learning models. Now, the learning models come with learning algorithms. So we have, for instance, learned the perceptron learning algorithm in the initial, let's say, linear learning model, and also in the multi-output perceptron. But then you can quickly go to something more advanced, where you then have, for instance, backpropagation of error, if you remember, in the multi-layer perceptron, or as it is also called, an artificial neural network with 2 hidden layers. So I will not repeat everything that we have last time. Please go back to lecture 6. The importance to take away, however, out of this was the number of parameters, and we will come back to this today in lecture 7. That's why I make an emphasis on this. We remember the multi-output perceptron based on this simple linear idea of a neuron or of one perceptron. You combine them. You basically have then learnable parameters, which were 6,850. So this is something what a CPU still can do. And then when we go to this idea of putting then these neurons in different hidden layers and interconnect them all, using then the backpropagation of error to go back to the inputs and basically analyze them and make an update of the learning and the training here in all the different weights, we come to a parameter setup with all these different weights that you see here. Instead of, just this dense layer, we have now much more dense layers here. We come to roughly 120,000 parameters. So you see a massive increase essential in all these trainable parameters due to the fact that we have dense layers. So everyone is connected to the, let's say, neuron in the next hidden layer and so on, making it a dense connection. So, and a bit in your assignment, you should explore this, that, this is a computing which is not so massive. However, we also understood then in the second part, two things. Firstly, deep learning is not just now adding the idea of one more hidden layer, one more hidden layer, one more hidden layer. I was repeating this, come back to this again today to make that clear. Deep learning is also adding smart layers, and the convolutional neural network was one example we focused on to make the point from the same, let's say, example that we have in the more or less what we call today shallow learning, right? So artificial neural networks, just two hidden layers. Basically that is considered maybe today rather shallow learning, while we had then here convolutional neural networks with much more layers, but then also having this interesting aspects of this different functionality that the convolutional neural network entails. And that was essentially the idea, firstly, that we keep the input in 2D, where there was no need to, vectorize or do a very long vector as input. But then we had also the idea of this convolution operations and, basically this creation of features, the feature learning that really make deep learning a little bit a successful part as well. Together with, of course, the architectures, which are very well suited for specific elements that you need. Transformers for large language models. You have here, convolutional neural network, very good for vision. And the idea of this kind of features that you learn was best captures, I think, with the visualization that I also encourage you to really try yourself. You will see interesting insights where you see really the different feature maps here, but also in the end, this typical dense layer where you have the softmax probabilities again, where you then essentially perform the real classification in the end. Is it a 7 or is this a 1 that is a bit like, not straight? Hence, we have to pay the price for it, which is now the idea of connecting it to lecture 7. So basically, we talked about 1.2 million parameters suddenly, right, that we have to train. And your assignment will then quickly show that CPUs are at the end of such a simple network. And this is just a very toy network. Some of the deep learning applications that we will have in the second part of this lecture will show you this. And I'll make also the case to large language models here in this lecture a little bit. Where we basically understand we are talking about billions of parameters, right? So this is interesting. So one takeaway message also was, of course, we can improve. So the idea of multi-output perception was around 90% after 20 epochs was this simple learning model. Of course, maybe there was some room of improvement using then the neural network with two hidden layers. And we actually got better performance, quite nice, with 95% performance, which is quite good already, right? And then we even topped that with a deep learning model now with 20 epochs, which in a way stands for many classes of deep learning today. So by far, I would say deep learning in vision recognition and speech recognition has been surpassed everything which was there before. So deep learning is the modus operandi. And with this also having perfect performance. However, 99.36 on a toy problem, on a simple problem we have here with 10 classes, handwritten characters, shows you also one limits of these learning models. And this is that, crap, what we put in cannot be learned. So we talk about rubbish in, rubbish out. So in other words, there's some of the classes we have seen the handwritten characters which are so not recognizable even for us humans that even machines would never understand it. And as such, can never achieve 100% because there's some noise in the data in a way. And if you have a practical application problem and you achieve 100%, chances are also that you are basically doing overfitting. Hence, the last lecture was a little bit short on regularization and validation. Both are there for combating overfitting, which you should learn in a proper machine learning course. So hence the idea also today, when I don't talk about distributed deep learning applications, again, about learning models, this is of course not something where, I can give you a complete machine learning walkthrough. So I encourage you again, go if you're interested and take really a machine learning course. Where are the fundamentals? statistical learning theory, the law of large numbers. You have basically Vatnik-Scherbonenkes dimensions, VC dimensions, things you have to go through to understand a little bit the capacity of a model versus essentially the size of the data you also have to bring. I come to this a little bit today. Of course, for large data, we need more GPUs, hence this distributed learning training. But we will start again with lots of things you know already a little bit, but from different lectures, and we pull that all together now for foundation and motivation, why we do distributed deep learning, why we have to do it, what is now the driving factor of it. And here are some examples, of course, from remote sensing, but also large language models I want to show you. And then it's important to understand a little bit the difference between learnable parameters and hyperparameters. So this is an important part of this lecture as well. And then we come again back to things like NCCL from NVIDIA. So libraries, communication libraries that we need then essentially across nodes and for GPU to GPU communication, like also the hardware supports that is really there with NVLinks and NVSwitches. In the second part, then we turn to the real techniques of deep learning in a distributed fashion. So there will be two major models, you would say, which is a data and model parallelism techniques for doing distributed training of deep learning networks. And we often talk about training because this is where the real, let's say, computational intensive part is located. When you do inference, once, let's say, a deep learning network is already trained, and then do inference, this is rather cheap and not so computation intensive. So the training is really the challenging part, and we will make the case for it, how we do it, and go much more in detail like we had in the last lectures on GPUs and deep learning. I will also provide you with some limitations of this. So there's a problem of large batch sizes we have to talk about, where essentially we can scale up higher and higher, in theory at least, but we will see, unfortunately, at some point in time, the accuracy will drop significantly. So there are some limitations in the route of how we distribute the data and the batches. And as such, we see the limitations of, even if we have, let's say, theoretical, maybe 16,000 GPUs in a system like Leonardo in EuroHPC, we may not use them all because essentially we as machine learners are also interested in the accuracy, or let's say the lower error rates. And if we continue to do, let's say, more and more GPUs, train with them, and the accuracy is going down, that is not helpful. Hence, we have to also carefully observe these limitations and see with this also some more or less drawbacks, that we have the whole machine, but we cannot use the whole machine as machine learners. And this has really dependence on the data, has dependencies also on which of the applications. Hence, we give you some different application examples. One of this is, of course, remote sensing, where we're quite strong from the research group, but also other application domains. And then in the end of this second part, then once we come there, there's another framework we should talk about called DeepSpeed. This is a more recent framework. And there are, of course, other distributed deep learning frameworks that I should mention here for completeness. Hence, if you are ready with this, you really have a much better understanding of scalable networks, of scalable, let's say, deep learning techniques for data-intensive workloads. And data intensive is important here because we want not to use GPUs more and more, while the, let's say, HBM and all the data within is basically so tiny that it doesn't make sense anymore to do this. The GPU, scalable variant of having, let's say, 8, 16, 32, whatever GPUs added, right? So this is an important part. So you understand not only scalability, but also the limits of scalability here after this lecture. And then, of course, again, the idea is parallel computing on various levels, from NCCL, which is really low level network communication library, to high level with PyTorch implemented, or even with TensorFlow combined with Horowat, complete different level within Python. And then you use, model load for NCCL, and it's automatically there implementing, funnily enough, things you already know from MPI, right? Making the connection again to certain foundations really of these applications, like the all reduce we will learn again today from MPI implemented, is something you already have actually seen in the beginning of this lecture. So in this sense, you have a understanding then of HPC programming paradigms for machine learning and deep learning in a scalable way, right? So this is something really what you can get out of here, and you have all the tools. You can go ahead and basically implement this. And with your HPC machines in the union, chances are that where you go in the, let's say, after your bachelor's or master's, you will basically also have the chance to use bigger HPC systems because they're there in the union, at least for industry and also academics alike. So let's go a little bit to some lectures and materials you already know, some slides you already know, but I need to get the foundations right and to connect them now to the other lectures we had, not at all together. And there would be a certain theme with it established, which I also would like to motivate then this distributed learning with. I mean, we started in the course very early of understanding now the GPUs. We had this many core concept. So, we had said, okay, it's not a cutting edge CPU anymore with, cutting edge processors. It's like just thousands of, let's say, moderate processors. But the good news is high throughput. We had this device memory and so on and so on. So I think by now you have understood the GPU, and we have understood that the, let's say, nicely parallelization of several applications that we can do there, especially in deep learning now, what we had also the last time in lecture 6, right? The learning of a car, the learning of a cow, the learning of a cat, whatever, is basically characterized of going back and forth through this network, especially then a variant of backpropagation if you want to update the weights again. And this is basically done, of course, with lots of matrix multiplications or matrix vector multiplication of some sort. And for this, of course, then the GPU is really perfect. And in this such shows you also the evolution of the GPU architectures we had the last time, really reaching from Kepler, Pascal, Volta, Ampere, Grace Hopper, and now the Blackwell architectures. And of course, this is fueling money to NVIDIA, right? Which is an important part here, that essentially this rise of deep learning also gave, of course, new applications that in turn require GPUs to advance in technology and making it more and more affordable to many more users. So this is a nice circle. And we also don't need to play now the video I have here for you. You remember this to understand now the feature maps and so on. We have done this in the let's say in the review of lecture 6, but now I want to also increasingly get you aware of, again, the learnable parameter aspect that will be now becoming key in thinking about that you have to go distributed. And if you remember, we talked about 1.2 million for this, kind of convolutional neural network example. And even this is not much if you now consider really large language models and so on. But we have seen that by adding, let's say, these smart, kind of layers, we quickly accelerate in, or basically increasing the size of the deep learning model substantially in terms of learnable parameters, right? So everything what we have there, the different layers and the convolution for the different features is nothing else than different matrices that we have to learn over time, basically through these iterations. And we do this via batches and then epochs, right? And this is something what you will also learn a bit in your assignment, a bit, I hope also stimulating then the idea between the multi-output perceptron artificial neural networks, not so computationally expensive. And then with deep learning, you quickly go into the realm of many learnable parameters. And with this, we need, more computing capacity. Now, this was one element where, okay, we had 1.2 million learnable parameters. And now we are in an era where I think many of you, and normally if I would be now in class, I would ask you who has used ChatGPT. And I think almost today, you don't find any student that has not used ChatGPT. And in this sense, I think everybody of you is familiar probably what ChatGPT can do. Not only, chatting around and so on, it can do this image recognition, so generative AI, which is a big theme today also for, let's say, deep learning models, which it intensively really require computing capacity. And there you are at the end with one GPU, right? So this is what I want to motivate here between this, what you basically can still do in your assignment with one GPU. When you are in the realm of large language models, and you see a little bit here the parameters, then you really need multiple GPUs and not just a few of them. You see here essentially small modules which are smaller than 100 billion parameters, right? Smaller is, let's say, something very funny if you come to a concrete architecture like here, where we said like, oh, it's 1.2 million. But of course, think about the complexity, what it entails to chat, to understand natural languages, which is, of course, then a complete different scenario or use case if you want to just differentiate between, let's say, 10 handwritten characters. So hence, we have here a bigger problem, and a bigger problem needs a bigger model. And the problem in this is that then this bigger model needs also bigger data. And I come to this and summarize this for you again with one slide you already know a little bit, but make the connection now to those learnable parameters. So the key message to take away is, of course, bring us also to the TrustLM project here that I see, that I provide here you for where also Iceland is involved. The crux is in the data, and we need more and more corpora of these languages to learn well. Let's say if you want to have language translation tasks, right? So from Icelandic to English, now people would say, well, there's Google Translate, but for Iceland, this Google Translate is actually not working quite well all the time, right? So it is already a good start to understand, no doubt, if you have no clue from the language, but the experts in Icelandic can tell you that, well, some of the translations are not very nice. Hence, there's also an idea to improve this, but the problem to improve this and why basically Google and the big players, right, they don't succeeded in this is that Icelandic and many other languages, Faroese, for instance, is not a corpora-rich language. In other words, you don't have so much text to learn from, right? And this needs to be in connection seen always, which brings us a bit to the foundations of statistical learning theory. Again, you need the right amount of data for the capacity of the model. And here we're talking about large transformer models, something I will talk a little bit in the second part of the lectures, but requires usually 2 university lectures as such, with attention mechanisms and so on, which really fuel these large language models today. And they have, let's say, as you see here, not only small billion parameters, they have also huge billion parameters, especially those which are well known, right? So the DeepMind model, for instance, was quite known, Palm, and so on. And even GPT-4, I mean, some of you know GPT-3 has 175 billion parameters, right? It's from OpenAI, the people that also do ChatGPT. Hence, growing, you see they were starting at 1.5 billion, suddenly 175 billion. And you can imagine that GPT-4 now has, massive amount of parameters. And this is where the computing capacity now is required. This learnable parameters is now the idea. Now briefly to the TrustLM project. So this is a project we obtained here in Iceland together with many partners in Europe in order to enhance large language models for Icelandic, for, let's say, underrepresented languages in terms of corporas, so also Faroese and so on. So our natural language processing lab headed by Hafstein Einarsson, we both did the proposal together with many others in Europe, AI Sweden, for instance. And, we have a couple of PhD students now working in this project in the HPC Competence Center with TrustLM. And we also collaborate, which is a worth note point here, with a language company, or one of the language companies here in Iceland called Miðeind, right? You see the logo here. So for those of you who are much more interested in the Icelandic language, as Icelanders here maybe in the course, firstly, I would encourage you to, talk to Hafstein and, the colleagues. They're really the expert in natural language modeling, where I'm more the expert in HPC alongside. While on the other hand, of course, Miðeind is an interesting company here in Iceland, really working hard of, getting Icelandic really, forward in terms of digitalization, how it can be used in computers, together maybe with another organization like Almannarómur. For those which are interested, should also look at this association driving Icelandic also in the country and elsewhere. So, but the key message again for the course now is large language models, lots of parameters. Hence, we add this a little bit now to our diagram we already know, right? So brief review, not very long, large data sets. Our serial methods are at the end. The traditional learning models don't help us anymore with large data. We can sample out some data, but still we would not have the comparable performance here. And this is not true for small data sets. Hence, having a large language model with very small data is a problem. Alluding a little bit already to what I said with Icelandic, right? You just don't have this big data like in English data sets and so on, right? You have maybe Icelandic data being rather somewhere here. So, and you want to improve like with human in the loop approaches for large language models and so on. And large language models are just one example. For many other vision problems, you also use transformers with many, many parameters. Just the large language models are maybe the king in terms of learnable parameters. That's why I put here plus, 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 right? So there's essentially no end if you see the slide before. And by going through these learnable parameters, you will see that the footprint for training time requiring HPC is constantly growing. And with this also now motivating the demand of going, in a multi-node, setup of learning this large language models. You cannot do this with one GPU, or let's say with one node with 6 GPUs. You have to go multi-node. And this is something, of course, what is the idea now in this course? Just a differentiation. Because firstly, we'll have another lecture on it, in lecture 14 on hyperparameters. And secondly, it's to understand that the learnable parameters are something different, right? The learnable parameters where the interconnects, the weights that we learn between the different layers and so on. And when we talk about hyperparameters, we have elements that we choose as humans, right? You see here some examples, the learning rate, that you have also in your assignment, right? And also batch sizes, a number of epochs, the optimizers, Adam, SGD, different variants are existing. Then the whole idea of even, let's say, creating the convolutional layer on sizes. You see this a little bit here in the two publications we do, essentially from our research, where you basically very fast have a huge space where we would say optimization space where you want to get, the best performance for the data at hand. And all the changes, and that's now an important part, please listen, all the changes I do here may affect the accuracy again in all the trained weights. In other words, when I, train with a, activation function rectified linear unit and then switching those to another one, maybe in all the different layers, then I have to retrain again and maybe get a completely setup of weights of the learnable parameters. So the HPO is the idea of this. We will learn this in lecture 14 in a systematic way. It's reaching even in the domain of so-called AutoML, that you also try to, let's say, automate the process of learning and creating specific architectures, right? Which is now a key element, of course, in thinking about HPC again, because here to find the best parameter setup is now the key. So you not only train these large language models or this large, remote sensing models we have seen here as an example, we also thinking about tuning these, hyperparameters better and better. That means we have to retrain, or we have to train at the same time. And with this, we have again the need essentially for, basically lots of computing power that we need. I gave you already an example from our, let's say, research, which stimulates a little bit that you have also, or need to have the data for it. Here's the big EarthNet that you, for instance, can use, which has different image sizes, and it's essentially a land cover classification problem with multi-label. So you see that a little bit here again, and this example I already was introducing to you. But of course, here you have also an example that then stimulates the idea of this is something what we can't use with one little GPU really, or we have to pay the price in terms of time. So we used here a ResNet 50 architecture, so which also has already an idea of the parameter growth, right? When you think about the MNIST, when we were at the convolutional network, and this is also still a convolutional network, let's say modified with residual connections and so on. And this is already, let's say, in order of magnitude more. We talk about 25 millions of trainable parameters. This interconnects here. These connections from one layer to another will be all learned, which are these 25 million trainable parameters. Hence, when you use a sort of cutting edge architecture for convolutional neural networks, you would say ResNet 50 is such one which stand the test of time, quite good for image recognition, combined with the idea of how much computing you put in. It's basically a good trade-off, right, between the accuracy and then the number of parameters, which stands essentially for the computing time you have to invest in it to train it, which is an important consideration, reaching in the idea also of green energy, energy computing, energy-aware computing, and so on. We have to think about also in later parts of this course. At the end, we will have a small reflection on this, because even if you have the best cutting-edge architectures, is it really worth to train it to get, let's say, 1 or 2% of accuracy, right? Or let's say the speed is a little bit faster, but I paid the price for significant computing. It's also something to think about when you see this rise of trainable parameters. And you can reflect on the large language models there as well. You know, we have seen the billions of parameters, and if you now have a language already spoken relatively nicely from a ChatGPT client or bot, questions remain if you now increase the parameters more and more, and the amount of computing, in other words, energy that goes into it, will it really improve the language significantly? And you would see that, for instance, in Icelandic, that would be probably not the case because we don't have even data for it. But even if you're swimming in data with English and many others, there might be limits where some things might be not really learnable, or where basically some things are getting us to a point where we have almost no increase in accuracy, but we spend much more energy. So is there a limit of having more and more, let's say, billions of parameters added in, let's say, GPT-5 as an example or so, coming up down the range? That is, of course, something for discussion and depends maybe also from language to language and in this kind of considerations. However, ResNet is now one example here, which already gives us a good motivation for this distributed training, right? Remember, we are talking now about training, so updating the weights. And we have learned this, for instance, in the lecture 6, this is done with the stochastic gradient, let's say optimizer, for instance. It could be Adam instead of momentum. There are different ways how you can do it, adding it so that you learn from this model iteratively, which we are having as a training process. And this here is one where we have a data parallel idea that essentially the data will be distributed across all of these different, having the same model. And of course, then when you have the same model here and just the data is differently, you actually have to communicate the update of the learning process with a technique called MPI or reduce. You already know. Right, so this is now the idea with multi-node, and you see on the left side doing an example here on juvels that we have already introduced. You can see that you can significantly speed up here the problem quite significantly of having maybe 24 nodes times 4 GPUs. So you use 96 GPUs. You also see limits again already, right? So it seems like I cannot just add more and more nodes here because then essentially I don't get any more big speed up. And this is, of course, something where we find different limits, which we also will catch up later again in the, let's say, second part of this course today. This is just one example. For instance, Horowitz is one of the frameworks we will motivate basically in the second part, and we'll also go deeper. I just wanted to make the connection now to the idea that we need to communicate now between different nodes. And this means we need also support for it on the software libraries level, but also on the hardware level, right? How the interconnect is done. Hence, we go back a little bit to things which are now more on the network interconnect level. And here's one good example of the NVIDIA collective communications library. So this is, let's say, sometimes called the hidden secret of NVIDIA. So why it's so performant? Because it has this nickel library very well implemented of inter-GPU communication that you will use exactly in this process I just meant here, right, with Horowitz. That's why I put it in. And the interconnect, of course, has now relationships to how you really interconnect the nodes. You see here in the single node performance, that doesn't matter, but you have already the NB links. But do you have also maybe InfiniBand connections, right? And you see here different, let's say, generations of NVIDIA technology in a multi-node setup, giving you also certain bandwidth, much more higher in a multi-node performance. So these are all relevant aspects to think about, that Horovod is, so to speak, the Python implementation of a distributed deep learning idea, which is based on reusing, of course, what we have in terms of network libraries. Now, this particular example, because they're all GPUs in these different nodes, which are from NVIDIA, we can use nickel. This is not the case, of course, if you have other accelerators. So it's a bit biased now again on the NVIDIA. But of course, you know, also, I talked about this before, the Euro HPC systems in the Union, many of them still have NVIDIA GPUs. Here's one example I brought to you, the Leonardo system that I already mentioned here and there. It has, you know, 14,000 GPUs, right, of the NVIDIA Ampere architecture. And now the good news, you would say, well, then let's use them for AI, right? All the 14,000 roughly. But you have seen the limits, and we will talk about the limits also in the second part. You can use a multi-node setup, but you probably with an AI problem can also reach to limits. Maybe not so in the large language models. They could probably fuel a lot of these systems quite up. And in this sense, this is something where really the connection can be made now between, you know, a large cluster system, many racks with nodes having all those GPUs here around 14,000, which excellent performance, but not only basically having now the accelerators, which do the job in terms of computing the many core, also the interconnects are usually very well in these systems. And from practical perspective, how you would use this, you don't even see that. You still program Horovod, and you have some small configurations maybe, but usually you just do module load, and you have this different implementation like cuDNN, for instance, for deep neural networks based on a specific CUDA version. And also, as I told you here, with a nickel library for implementing, for instance, MPI or reduce very well for accelerators here. This is something you want to load, right, in a module together with the CUDA version, which you remember is the NVIDIA, let's say, programming model. And this is an example of this system, Leonardo HPC system, in terms of which models you have to use when you want to execute on PyTorch-DDP. So hence, there's also another deep learning framework we're going to talk about in the second part much more, that is doing similar aspects, data parallel, and this is also now what we also have to question. So what about model parallelism, right? And you will see in deep space, a new framework has also other ideas. Now, there's one thing we left a bit out here, and this is again then the relevance of the NB links and NB switches, which I talked about already in lecture 5 a lot. So I don't want to repeat everything. We had there used the Summit architecture, although Summit is decommissioned. There's lots of good material here for teaching, where you can see that a Summit node, number one in the supercomputing, had, for instance, 6 GPUs per node, right, in a dual core architecture here. So in this sense, you have essentially this idea that these GPUs are very well interconnected with an NB link. In other words, GPU to GPU, right? What we need basically within the node, and then, communicate very well, and enables us then with so-called NB switches to really communicate, all to all, what we need in all reduce, if you remember, right? So this is, of course, the MPI all reduce idea, a collective operation, which is having the idea like we had in MPI reduce, but then the all reduce is doing the same job for everyone involved in the communicator. And all of this is basically then making you the connection now. Hopefully you will understand from the high level Horovod framework or PyTorch-DDP, in the end it doesn't matter, over the network interconnect that you have across the nodes with InfiniBand, for instance, in the usage of the node, using NB links, using NB switches as shown in this particular one, where you then see also significant, let's say, evolution of these bandwidth that we need. So again, it is about data in the end, right? We want to, average, for instance, gradients, the learning progress. Or what we want to have is also having data loaded into the GPU. Hence this slide, what I had also already given to you before, shows you again the interesting aspects that we have in these different architectures from Volta up to Blackwell, which is the most cutting edge one in the moment, where the NV switch GPU to GPU bandwidth is significantly increasing. And I brought you a video to understand a little bit this in terms of NV switch, NV links, what that means, and how many you can have is of course a very important consideration. And you see a growing, let's say, scale performance here, even with the more next generations that we will see with the Blackwell architecture. And I think that's all I leave you on the table today. Of course, now you can go in different, more details of technology, but we want to understand more distributed deep learning techniques and some applications and context in the second part. It's still beneficial maybe to look at this video. Again, I'm not paid from NVIDIA. I just think it's a good illustration to understand now where NVLink is coming from, and why it's of course now important to think about this technology when you scale up your deep learning algorithms. So we make here a small break and then come back to the distributed deep learning techniques, really combined and fueled with some interesting more applications.